Histopathologic cancer detection is notoriously difficult. Tissue variability and staining artifacts make classical edge detectors unreliable. They amplify noise while missing diagnostically critical boundaries. Previous quantum approaches relied on global amplitude encoding and quantum Fourier transforms, but those require full state vector readout, which simply doesn't exist on real hardware. So how do we run quantum edge detection on actual NISQ devices? We replace global encoding with local, single-qubit Ri-angle encoding. Each pixel maps to a point on the block sphere via a y-axis rotation, requiring exactly 1 qubit per pixel with no preparatory entanglement. Edge strength is computed using a dual gradient overlap primitive. Instead of sequential measurements, our DGCSWAP circuit runs horizontal and vertical gradient estimations in parallel across a 6-qubit register. Measuring the ancilla qubit in the excited state directly yields the edge magnitude via the swap test probability. NISQ hardware is noisy, so we prove algebraic equivalence between the DGCSWAP circuit and a shallower ancilla-free DGDSD circuit. The DSD variant compiles down to just 2 native CNOT gates, perfectly matching superconducting and trap-tie-in device topologies. We then apply a 3-stage mitigation pipeline, readout confusion matrix inversion to correct spam errors, piecewise interpolated bias subtraction to remove the hardware noise floor, and global slope regression to fix visibility attenuation. This cuts single-pixel hardware mean squared error by roughly 8 times. We validated this across 5 real quantum processors via Amazon Bracket. Interplatform correlation sits between 0.93 and 0.94, proving the estimator extracts a hardware-agnostic signal. When fed into a single RaisNet 50, the quantum edge map achieves 79.8% accuracy on the patch Chameleon benchmark, boosting sensitivity over unprocessed baselines while maintaining specificity far above classical methods. A lightweight configuration delivers a 17 times per processing speedup, with only a 2.6% accuracy trade-off. This is the first hardware-validated quantum preprocessing pipeline for histopathology, with practical, multi-stage NISQ mitigation. The full protocol and cross-platform results are in the linked paper. If you're working at the intersection of quantum computing and medical AI, this framework gives you a reproducible baseline for noise-aware quantum image processing.